Okay, so let's take a look at problem 4-43. This furnace again, more specifically, the mechanism of the handle controlling the furnace door. We looked at this problem graphically, so let's go ahead and let's take a look at this analytically. So, analytically determine the linear displacement of the furnace door in the mechanism shown in the figure, as the 26-inch handle is rotated 25 degrees counterclockwise from its current position. So, to set this up, we first need to get a bearing on the location of where our furnace door is right now, and we're going to do that in reference to this pivot point here. So let's start by drawing a kinematic diagram of what we got going on. So we'll draw that pin being on the ground. Go ahead and we'll label our pins up here. I will go draw the furnace box itself with this frame like so. We'll make it clear that this frame is on the ground. We'll go ahead and we'll just highlight this as our slide-in joint. Okay. So let's pull this out. Look at it over here. Okay. So let's go ahead and let's label a few things. More specifically, let's look at this 10-degree angle right here. So if we imagine a line horizontal through that handle pivot point, we can go ahead and call this angle theta 1. And now let's label what we're actually looking to find. So let's look at the initial displacement of where this last pin is. Let's go ahead and label these pins too. Joint A, B, C, and D. Just to have some frame of reference here. So let's look at the displacement of that pin C. How we're going to do that, let's just go ahead, if we draw a horizontal from C, and then a vertical down from A, this distance between this horizontal off of C and A, we're going to call RC. And that's going to be our linear displacement. So let's look at solving RC in our initial configuration where theta 1 is equal to 10 degrees. We can actually just theta 1 equal to 10 degrees. So the first thing that we probably need to look at solving is the angle in which this bar BC is oriented. So if we draw a vertical off of it, then we can call this angle it makes theta 2. Okay, so if we look over at the figure, it gives us this distance between pin A and pin C in the horizontal being 9 inches. So that's something we can work with. So let's look at trying to solve for theta 2. So theta 2 is equal to, now if we kind of take a look, we can call this distance, right, that bar BC moves in the horizontal. So between pin B and C in the horizontal, that is, we'll call that length L. So theta 2 is equal to the inverse sine of L over length BC. if we go ahead and we expand this to find length L, easy enough, we can remember some trig here, making things into triangles. 9 minus 8 cosine 10 degrees. Right, and so really we're just taking this overall length 9. And we know that this pin is located at the end of this handle. And we know that from pin A to pin B at this 10-degree incline is 8 inches. So to put that in pure horizontal, we just need to go ahead and we need to take 8 times the cosine of 10, we get 10 degrees from our theta 1, because we can also say that theta 1 is this angle as well. So 9 minus 8 cosine 10 over top BC, which is 15 inches. I got ahead of myself. Sine inverse. So this gives us 4.29 degrees. So theta 2 in our initial configuration is 4.29 degrees. Okay, so if we're going to look at, right, coming back to our original, what we're solving, right now we're looking for RC. So RC is nothing but this length BC taken in the vertical minus the vertical length AB. So RC is equal to BC cosine theta 2 minus AB sine theta 1. And this gives us 15 cosine 4.29 degrees minus AB is 8 inches, 8 sine 10 degrees. And this gives us RC in our initial configuration equal to 13.569 or 57 inches. So now we have our initial configuration, so we need to figure out our displaced configuration. So the displaced is nothing more than taking theta 1 and adding 25 degrees to it. So now theta 1 is equal to 35 degrees. And we just will run through the same set of calculations we just did. So theta 2 is equal to the inverse sine of 9 minus 8 cosine 35 degrees this time over 15. And that gives us 9.39 degrees for theta 2. And then in our displaced configuration, we'll go ahead and we'll call this theta 1 prime. Sorry, that's theta 1 prime, and theta 2 prime. So then RC prime is equal to 15 times the cosine 9.39 degrees minus 8 sine 25 degrees and that's equal to 8.25 inches. So then the change in RC, delta RC, is equal to RC minus RC prime, which is equal to 13.57 minus 8.25, and that gives us 5.32 inches of displacement.